Hello everyone. Today I will be presenting my project on building a real-time EV dashboard and advanced driver assistance system. Because this is an online internship, we are simulating a real-world automotive environment. My objective for this presentation is to walk you through the journey of how we collect analog sensor data, process it using an embedded microcontroller, and transmit it to a live Python dashboard to emulate the exact behavior of an electric vehicle. To start, let's look at the system architecture. In embedded system, we have a host and a target. My laptop acts as a host where I write and compile C code using the STM32 cube ID. The compiled binary file is then loaded onto our target, which is a simulated blue pill board inside a tool called PiximLab. This board uses the STM32 F103C8T6 microcontroller. It is built on the ARM Cortex M3 profile, which is highly efficient, low cost, and specifically designed for general purpose microcontroller applications without an operating system. Since we don't have a physical car, we must simulate our sensor data. We mapped 4 potentiometers to the microcontroller's pin, starting from PA0 to PA3. These potentiometers act as variable register, allowing us to simulate the driver pressing the acceleration pedal, hitting the brake pedal, the battery's state of charge, and the motor temperature. For the ADAS module, we use three simulated ultrasonic sensors to calculate the exact distance of obstacles in the front, left, and right of the vehicle. The real world is analog, but our STM32 microcontroller only understands digital language, that is, zeros and ones. When I adjust a potentiometer, it outputs a voltage varying from 0 to 3.3 volts. To read this, we use the microcontroller's internal ADC or analog to digital converter. Because it is a 12-bit ADC, it maps that 0 to 3.3 volt range into 4096 discrete steps, meaning we get a digital reading from 0 to 4095. Once we have that raw number, our code scales it down into a clean percentage from 0 to 100 to represent pedal presses. In standard C programming, you might use a delay function to pause the system. However, in an embedded AV system, a delay entirely blocks the CPU, meaning the car could not sense a sudden obstacle while waiting. Instead, we use hardware timers. By configuring the timers, prescaler, and auto reload registers, we can divide the 72 MHz clock to generate an interrupt at an exact frequency. Our project requires strict timing. We must pull the pedal every 10 milliseconds and we trigger the ultrasonic sensors exactly every 100 milliseconds. When the timers overflow, it triggers a callback function, pausing the main loop just long enough to read the sensors without missing a beat. To control the hardware, we cannot simply write pin 30 equals 1 in C. Instead, we use ST Microelectronics Hardware Abstraction Layer or HAL libraries. This predefined function allows us to easily interact with the board's complex memory register. For example, we use HAL ADC gate value to read the potentiometers. Similarly, HAL GPIO toggle pin to blink our warning LEDs and HAL UART transmit to send our calculated data to the outside world. Once we read the analog pedals, we apply a physics-based inertia model in our C code. We calculate the motor's torque, the resulting acceleration, and the vehicle speed. As the speed increases, the code calculates the power consumed and actively drains the battery's state of charge. A major feature we implemented is regenerative braking. If the brake pedal is pressed more than 5%, our code generates negative torque instead of draining the battery. This negative torque is redirected to actually recharge the battery, simulating how real EVs recover energy when slowing down. For the ADAS module, we ping the ultrasonic sensor's trigger pin high for 10 microseconds and measure how long the echo pulse stays high. Using the speed of sound, we calculate the exact obstacle distance. By dividing the front distance by our current speed, we compute the time to collision, or we can say TTC. If a front obstacle is less than 50 centimeters away, we issue an advisory warning. If it drops below 20 centimeters, it escalates to a critical alarm. Additionally, if the side sensors detects anything under 30 centimeters, we trigger blind spot detection warnings. To make the system safe and predictable, we manage the vehicle's behavior using a finite state machine. The car transitions through specific state: parked, ready, driving, and regenerative braking. For example, you cannot apply regenerative braking if the car is in parked mode. We also built a fault manager. If the motor temperature exceeds 120 degrees Celsius, if the battery drops below 5%, or if a critical collision occurs, the FSM instantly shifts to a vehicle into a fault state. When a fault is active, motor torque is forced to zero, completely stopping the vehicle to prevent an accident. To get this data out of the microcontroller, we use the UART communication protocol running at a speed of 1,15,200 bits per second. This acts as an industrial diagnostic port. Not only is the STM32 sending telemetry out, but it can also receive commands from an engineer. Because commands arrive randomly, we use UART interrupt to tie to a ring buffer. This safely stores incoming letters byte by byte in the background without pausing the motor control. Once a full command like fault clear is received, our shell process validates it and executes the request. Finally, we bring this data to life in a real car. The ECU talks to an LCD screen. Here we use a virtual serial port to link our simulated blue pill board directly to a Python script. The Python code runs two parallel threads. The first is a serial reader that continuously catches the UART test strings and parses them into usable numbers. The second is an animation loop built with the matplotlib library. 10 times a second or every 100 milliseconds, it pulls those past numbers and automatically redraws the speedometer, the battery bar, and the ADAS bird's eye view. In conclusion, this project successfully emulates the core brain of an electric vehicle. We bridge low-level embedded hardware concepts like ADC, hardware timers, and UART communication with high-level software processing and UI design. By applying physics formulas and strict safety state machines, we created a system that reacts identically to a real car. I will now transition into a live demonstration of Pixim Lab environment and the Python dashboard in action. Thank you. Now let me explain the host side of my project. The host is the system where I develop the entire embedded application. In my project, my laptop acts as a host and I use STM32CubeIDE, which is the official integrated development environment provided by ST Microelectronics. STM32CubeIDE combines three major functionality into one software. First, it allows me to configure the microcontroller using STM32Cube Second, it provides an editor where I can write my embedded C code. Finally, it compiles the entire project and generates the executable binary that runs on the STM microcontroller. If we look at the left side of the IDE, we can see the Project Explorer. This contains all the files required for the project. The project is mainly divided into different folders like core, driver, startup, and debug. The core folder contains all the application code that I have written. One of the most important file in this project is this .isc file. This file is created and managed by STM32Cube MX, which is integrated into STM32Cube IDE. Instead of manually configuring hardware registers, I use this graphical interface to configure the microcontroller. For example, in my project, I configured GPIO pins for LEDs and ultrasonic sensors, UART1 for serial communication, timers for periodic task execution and sensor timings, clock configuration for the STM32F103C8T6, and pin assignment for all the peripherals. All these settings are stored inside the IOC file. Whenever I save this file, STMCubeIDE automatically generates the required initialization codes such as GPIO initialization, timer initialization, UART initialization, and clock configuration. This saves development time and reduces the possibility of hardware configuration mistakes. Inside core, the first folder is INC, which contains the header files or .h files. Header files mainly contain function declarations, macro definitions, constants, data structures, and global variables. You can think of a header file as an interface. It tells other files what functions are available, but it does not contain the actual implementation. For example, in my project, ADAS.h declares function related to Advanced Driver Assistance System. Then avcontrol.h declares function used for electric vehicle control logic. Then fault.h contains fault related definitions and fault flags. Then ultrasonic.h contains function for ultrasonic sensor measurement. UART shell.h declares UART communication functions. Using header files makes the project modular and avoids rewriting the same declarations in multiple files. Next is the src folder. This contains .c files which contain the actual implementation of the program. If the header file tells what a function does, the source file tells how it does it. For example, main.c is the entry point of the application. Execution starts from main function. Here the peripherals are initialized and the infinite loop continuously executes the application. ADAS.c contains the logic for obstacle detection and collision warning. avcontrol.c contains the electric vehicle state machines such as park, drive, brake, and fault state. Then fault.c continuously monitors the system and detects conditions like low battery, motor overheating, or collision warnings. Ultrasonics.c reads the ultrasonic sensors and calculates the distance to nearby obstacles. UART sends all the important information like speed, battery percentage, temperature, and fault status to the serial terminal for monitoring. Separating each functionality into its own source file makes the project easier to debug, maintain, and upgrade. Once all the code is written, STM32CubeIDE compiles every .c file together. If there are no compilation error, the IDE generates an executable file such as .bin file. This compiled firmware is then loaded onto the STM32 microcontroller where it executes exactly as programmed. So in summary, STM32CubeIDE is the complete development environment where I configure the hardware, write embedded C code, organize the project into modular files, compile the application, and generate a firmware that is finally executed on the STM32 microcontroller. Now we transition from software to hardware because this is an online internship. We are using Pixim Lab as our hardware simulator. The target board we are using is the blue pill which features the ARM Cortex M3 STM32F103C8T6 microcontroller. In the module section, we have our spare parts simulating the vehicle sensor. We are using 4 potentiometer mapped to pins PA0 through PA3. This acts as a variable resistor sending 0 to 3.3 volts to the ADC. They simulate our acceleration pedal, brake pedal, initial state of charge, and the motor temperature. Here we have three HCSR04 ultrasonic sensors mapped to port B to detect front, left, right obstacle for our ADAS module. Also, we have our onboard warning LEDs. These act as a visual indicator for the safety system. We have a red LED to indicate critical front collision based on our time to collision calculation. We also have dedicated LEDs for blind spot detection on the left side and on the right side. Finally, we have a yellow LED acting as our fault, or we can say fault indicator, which illuminates immediately if the finite state machine detects a critical error such as motor overheating or the battery dropping below safe levels. Before sending data to a graphical interface, we must validate our calculation. We do this using input output virtual terminal, or we can say IoT virtual terminal. This terminal acts like industrial diagnostic port, catching plain text data transmitted by the microcontroller via UART protocol. In this terminal, you can see a continuous stream of both our EV and ADAS parameter. For the EV parameters, the terminal prints the physics-based calculation. This includes the vehicle speed in km per hour, the active motor torque, the acceleration and brake percentage, the remaining state of charge, the estimated remaining driving range, and the motor temperature. For the ADAS parameters, the terminal prints the exact obstacle distance in centimeters for the front, left, and right sensors, as well as it also shows time to collision and any active blind spot or collision alarm flags. This raw data stream proves our embedded C logic is functioning perfectly before we push it to the Python visualization. To get this virtual terminal data out of the simulator and into our Python script, we use a tool called Virtual Serial Ports Emulator or VSPE. VSPE creates a virtual cable, for example, pairing COM1 and COM9. The STM32 simulator transmits on one end and our Python dashboards listen on the other end. Now we reach the final stage, the Python dashboard. This script uses a serial reader thread to catch that incoming text data, parses it and uses the matplotlib library to redraw these animations 10 times a second. Let's test the vehicle's 4 functions. First, I will press the acceleration pedal. As the acceleration percentage increases, you can see the motor torque increases. The physics-based inertia model calculates the new speed and the speedometer gauge rises. Notice that as we drive, the power consumed actively drains the battery's state of charge bar and the estimated remaining range drops. Now let's test regenerative braking. I will let off the accelerator and press the brake pedal. When the brake is applied past our 5% threshold, notice that the torque becomes a negative value. Instead of draining the battery, the vehicle uses this negative torque to charge it. You can see the speed reducing while the SOC actually begins to increase. Let's test the advanced driver assistance system. If a vehicle enters our side perimeter, that is under 30 centimeters, our blind spot detection triggers. You can see the bird's eye view flag, an advisory alarm, and highlight the obstacle. What happens in a critical emergency? I will simulate a sudden object in front of the car. The time to collision drops to zero point 0.0 seconds. The system immediately triggers a critical collision alarm. More importantly, our finite state machine instantly shifts the vehicle into a fault state. Look at the motor torque. It is forced to absolutely zero, meaning the vehicle has safely cut motor power to prevent the accident. Let me clear the obstacle to reset the state. Finally, let's test the internal fault manager. If I simulate a severe motor overheating scenario, that is pushing the temperature above 120 degree, we can see over here the FSM flag fault code 01. Once again, the warning LED on our board illuminates and torque drops to 0 to protect the hardware. By connecting embedded C hardware control with a Python user interface, we have successfully simulated a complete real-time EV and ADAS electronic control unit. Thank you for watching my demonstration of project.